Bernd Finkbeiner, and I'm very happy now that Emma started the recording of this session. So again, if you don't want to be on this recording, close your cameras, or if you don't mind, keep them open. That's also fine. But Bernd Finkbeiner is our next speaker, and Bernd is a faculty member of the KISPA Helmholtz Center for Information Security, and he is a professor for computer science at Saarlandes University. He obtained his PhD in 2003 from Stanford University, and has since then been leading the reactive systems group, which is now part of the KISPA Center since 2020. The research focus of Bernd is the development of reliable guarantees for the safety and security of computer systems, and includes specification, program synthesis and repair, and static and dynamic verification. And he is the holder of an ERC consolidator grant. So I will hand over to you, Bernd. He didn't write that, but I know that, so it's true. He is the holder of an ERC consolidator grant.
Thanks very much, Kim, for the kind introduction and the nice addition to my biography. Only correction, it's CISPA, not KISPA.
Sorry.
All right, so thanks very much for having me. I would like to talk about hyperproperties, which are a truly exciting type of property. Many of you may associate hyperproperties mostly with security, but really they are just about anywhere. And I certainly have become very interested in hyperproperties over the last 10 years or so. And together with my collaborators, I have built several tools for verification, synthesis, and also monitoring of hyperproperties. So the term hyperproperties was coined by Clarkson and Schneider. Hyperproperties are a generalization of trace properties. A trace property is a set of traces, and we say that a system satisfies a trace property if every execution, if every trace is an element of the property. Now, a hyperproperty is simply a set of sets of traces, and we say that a system is correct if its set of traces is an element of the hyperproperty. Now, the single most well-known hyperproperty definitely is noninterference. So in security, we typically classify the inputs and the outputs of a system as either high security or low security. And we require that the low security output should not depend on high security input. So it should only depend on low security input. And now this is a hyperproperty. So we consider all sets of traces acceptable that have this property that if you look at two of them, if you look at T and T prime in this set of traces, and T and T prime happen to agree on the low security inputs, well, then they also must agree on the low security outputs. Now, non-interference may be the most famous hyperproperty, but it's by no means the only one. So in security, definitely there are many of them, in particular in information flow security. There are many notions of secrecy. There is quantitative information flow, there is differential privacy and the like. But there are also many hyperproperties outside security. So symmetry, for example, is one of them. So in an arbitration protocol, you might require that the waiting time of a client is independent of its ID. Well, that's a hyperproperty. Fault detectability. So if you have a coder, then you might want to require that encodings of different data should have a certain Hamming distance to each other. So again, you need to compare executions that result from different input data. So that's a hyperproperty. Robustness. Traces without significant difference in the input must have no significant difference in the output. Also, partial observation. The control strategy of a component should only depend on its explicit inputs. Or dominance. The actions of a control strategy should be as good as any hypothetical alternative. So this list goes on, and certainly each of these properties have a whole body of work in terms of verification techniques to them. But I think the big question is whether it's really necessary to look at all these types of properties which have the common feature that they are hyperproperties, if we need to invent verification techniques always specific to these properties, or if there is a more general pattern. So the challenge that I want to talk about is that we try to develop general specification logics for hyperproperties, mostly with the goal of understanding the landscape of hyperproperties, to understand which of them are actually the same and which of them are fundamentally different. And then on this basis, go ahead and build scalable verification algorithms that in a uniform way solve entire classes of hyperproperties. Now, our starting point some years ago was the logic HyperLTL. HyperLTL is a simple generalization of standard linear time temporal logic. The addition is that we have a prefix of quantifiers that allows you to refer to multiple traces at the same time. So let's say if you have this really simple system here on the left, just a black box with a light bulb on top, and this light bulb is flashing, but you don't want it to reveal anything about what's going on inside the box. Well, you can express that in HyperLTL by saying that for all traces pi and pi prime, it's globally the case that the light is on one trace if and only if it's on the other trace. So what the logic does is it steps through two traces simultaneously, right, the left one and the right one, and relates them at corresponding levels. And what we make sure is that it's the light is on one trace if and only if it's true on the other. Okay, now the nice thing about having such a logic is that we can now go through the literature and look at all these different notions, say, of secrecy, write them down in our logic, and then understand a little bit what's going on in these properties. So to give you a few examples, here's the classic notion of observational determinism, which means that if the low security input is the same, then globally it must be the case that the low security output is the same. This is a universal hyperproperty. You need two universal quantifiers for that. Now, non-inference is a similar but very different property because it is an for all exists property. It says that no matter what trace I start with, there is another one where I've set the high security input to a constant value, and yet the two traces agree on the low security behavior. So I've identified one particular alternative behavior with a different high security input, and yet its observable behavior is the same. And lastly, there's generalized non-interference, which is a for all exists property. So this is even more general than non-inference because I just pick two traces and I take the high security inputs from one and the low security behavior from the other, and yet there must be a third trace, pi double prime, that combines these two behaviors. In other words, the low security behavior is completely independent of the high security input. All right. Now, the bad news is it's a pretty expensive logic. So you see that the model checking problem is non-elementary. Essentially, you have to pay one exponent for every quantifier alternation, and that can give you an arbitrarily high stack of exponents. Now, the good news is we tend not to use too many quantifier alternations. So observational determinism, it's a universal property, so there is no quantifier alternation at all. So this is in this really inexpensive part of the complexity space. It's in the same complexity as temporal logic, so it's a non-deterministic log space. Non-inference, with its for all exists quantifier structure, is one exponent more. So it's in P space, and generalized non-interference has, well, the same quantifier structure, so it's also in P space. It's also the case that the complexity, of course, depends a little bit on the structure of your system. So this is for general Kripke structures. If you have a simpler Kripke structure, like acyclic graphs or trees, then the impact of these quantifiers diminishes. So if, say, you have a tree structure, then no matter what quantifier structure you have, it's always solvable in a deterministic logarithmic space. So it becomes very, very inexpensive. Now, HyperLTL, of course, was only the starting point for this investigation of logics. So here you see an entire hierarchy of logics separated into linear time and branching time. And the interesting thing is, as you add more features to the logic, new types of hyperproperties become expressible. So if you go from HyperLTL to first order logic, what you gain is the possibility to talk about uniform termination. That is, there is a common upper bound on all executions of your system by which they will have terminated. If you add quantification over propositions, then you get omega regular hyperproperties. You can say that only in every second step do I require the traces to agree. And if you go to monadic second order logic of one successor, you can describe Turing machines. Now, in the branching world, you get this fascinating ability to talk about the creation of information. So hyperproperties allow you to talk about the flow of information, and the branching allows you to talk about the creation of information. So by having both branching and hyper, you get to talk about information in very general terms. Now, monadic path logic then adds the capability to talk about knowledge. And if, again, we add quantification over propositions, then you have the full power of second order quantification. Now, it's not surprising that in this powerful hierarchy, not everything is decidable. So the good news, again, I think, is that a large fragment of this hierarchy actually is decidable. So in the linear time world, HyperQPTL, so the extension with quantification over propositions, seems to be the limit. This is where the model checking problem is still decidable. S1S already is undecidable. In the branching time world, it's monadic path logic that forms the limit. So we can talk about knowledge, but not about general second order quantification. Now, for satisfiability, the situation is a little bit worse. There, all these logics are undecidable, but they all contain interesting decidable fragments. So essentially, it's again the quantifier structure that makes the difference. If you have exists for all formulas, which are actually very important, then the satisfiability problem is decidable. As soon as you have a single for all exists quantifier alternation in your formula, the satisfiability problem becomes undecidable. All right, so this has been the background for our development of a range of tools. So MCHyper is a model checker. It's a hardware model checker. It accepts a fragment of HyperQPTL. EAHyper is a satisfiability decision procedure. So you give it a formula and it tells you whether it's satisfiable or not. MCHyper is a variant thereof, which, I mean, it accepts a much more general class of formulas, but it's not a decision procedure. It's just a model generator. So it will find a finite model if one exists, but it will not necessarily tell you that no model exists. RVHyper is a monitoring tool. So we can observe a running system and determine whether or not the hyperproperty is satisfied. And lastly, HyperBoSy is a synthesis tool. So you give it a description of the desired hyperproperties, and it generates a system that is guaranteed to satisfy these hyperproperties. So let me go a little bit through those tools. MCHyper, as I said, is a model checker. What I'm showing you here is its online interface. So you can go to our webpage and play with it as much as you like. We also have a tutorial and examples and so forth. So you give it a Verilog description of your system and a specification of the hyperproperty, and it will then either output a counterexample or tell you that the property is satisfied. Now, the basic idea of the model checker is to transform the problem. So it takes, as I said, a circuit description, then transforms the circuit so that the resulting problem is a standard trace model checking problem, and then it returns the result. So let me just illustrate that with a small example. So here we have a universal hyperproperty. If the inputs are the same, then the outputs must be the same. We negate this property in order to find a counterexample. So we're looking for two traces pi and pi prime, where the inputs are always the same, but there is a difference in the outputs. Now, we build a circuit that searches for such a counterexample. This circuit has three components. First of all, two copies of our system in order to generate two traces. Our two existential quantifiers look for two traces, right? And then the third component is a circuit that watches out for the violation of the specification. That is, it makes sure that the inputs are always the same, and yet there's a difference in the outputs. So the benefit of such a transformation is that now we're left with a standard verification problem after we have done this transformation. So we can use standard verification tools to solve the problem. And we just do that. In this case, we connect to ABC, which gives us access to IC3 interpolation, bounded model checking, and everything. And this is extremely convenient because, of course, all these different verification approaches have their strengths and weaknesses. So, for example, bounded model checking, of course, is incredibly good in finding bugs. So this allows us to look at rather complex systems, such as an Ethernet controller, and analyze the information flow in that system.
So Bernd, less than 5 minutes now, right?
All right, very good. Now, satisifability. Again, we have a nice online tool if you want to play with it. It accepts a formula and tells you if it's satisfiable or not. It actually, the most common use case is that you give it two formulas, and then it will analyze the implications between the two formulas in order to see if they're equivalent or if one of them is stronger than the other. So this is the major use case of a tool like this. What you find in the literature quite often is that you have a property that you think is the same, but it's formalized in different ways. So what you see here are two versions of observational determinism. One that says if the inputs are the same, then the outputs must be the same. The other one says, well, the outputs must be the same until there's a difference in the inputs. Now, are they equivalent or is one of them stronger? You can log on to EAHyper to find out. Monitoring. So the monitoring works like this. You observe a system over a long time. So you observe it in different interactions with its users. And each such interaction is a trace. And then you continuously model check the growing set of traces until you find a violation. So this is very interesting because in contrast to standard monitoring problems, you can't just forget things as you go through the trace, because everything you see in one trace may be relevant once you see the next trace. So the algorithmic problem here really is, how do you store the relevant information in a compact way such that the model checking gets facilitated as this set of traces grows. And there's a lot of technology that goes into this, SAT PDDs, prefix trees for traces, and a lot of pre-processing, in particular recognizing symmetry, transitivity, reflexivity, and so forth. So these are all problems that need the machinery of satisfiability and verification, but now in the context of a monitor. So the synthesis problem is very interesting because hyperproperties, of course, can encode various versions of synthesis that people have historically looked at. For example, the distributed synthesis problem, of course, is only a synthesis problem where you have the hyperproperty that your components only depend on their local inputs. Same thing for symmetric synthesis and various other variations. Now, not surprisingly, the synthesis problem is again undecidable. in general, and the fragment where it's still decidable is actually quite small. But what we can do is we can use bounded synthesis. That is, we bound the size of the solution and then find one that satisfies the hyperproperties. And this turns out to be very, very fruitful. Let me just show you a table from our benchmarks. So let's maybe just look at the last line, the dining cryptographers, right? So this is an interesting benchmark because it has a very intricate flow of information. So you have the cryptographers sitting in the room, and they each anonymously pay for the meal, and they don't want to know who was the one who paid, but they want to know if it's the NSA who may have paid. So if one of them has actually paid, right? So there's a very tricky kind of information flow specification. And actually our synthesis algorithm then gives you the standard solution to the dining cryptographers. So let me just conclude. Hyperlogics are a really powerful tool because they allow you to deal with hyperproperties, and that's interesting for security, but I think way beyond that. The hierarchy of logics is rich and interesting, and yet it has this property that verification is decidable for a large class, and even satisfiability can be done for a useful class of formulas. There are some exciting challenges around. So in particular, I think we're discovering more and more hyperproperties, some of them with amazing societal relevance. Think explainability, think fairness, and all these things. These are hyperproperties, and I think they will matter more and more as we go forward. Also, I think this is an amazing opportunity for program repair, because in synthesis, you always have this problem that you need to specify the functionality. But in program repair, you don't, right? You have a program that already tells you what your functionality is, and maybe then you want to add something like secrecy or fairness or symmetry, so you can try out if there's an equivalent program that has this additional property that you're interested in. All right, with that, let me just quickly thank my many collaborators and also thank you for your attention.
Thank you very much, Bernd. Nice presentation. So let me look in the. Maybe you should put up your slides again, Bernd. I think it can be nice to.
I will do. I just love to see you also. So,
oh yeah, you cannot see us. Then wait.
No, but I'll put them up the moment.
But I understand what you're saying. So while you're thinking about questions, I have quite some questions myself. So maybe just a small technical one. So does it these quantifiers over traces pi? Can you nest them? Can they be nested inside the modalities? I didn't see them in the examples. To me, it seems that it makes sense maybe in the branching, but not in the linear. But I don't know.
Yes, Kim, you answered your own question perfectly. Okay. So that's actually the difference between HyperLTL and HyperCTL star. In HyperLTL, you require the trace quantifiers to be in prenex form to have a quantifier prefix. So you first quantify over traces and then you relate them. In HyperCTL star, you can branch off into new traces at any point in time. So you do that by nesting temporal modalities and trace quantifiers.
Yeah. Maybe a last one before I hand over to Armin. So there is something called the modal mu calculus, which subsumes LTL and CTL and CTL star. I mean, wouldn't it make sense to take that logic and add hyperness to that?
Yes. So in fact, that has been done a long time ago. There's the polyadic mu calculus, which essentially looks at several copies of the system and then does the standard mu calculus thing about it. There's a limitation to it because you actually have a fixed number of copies that you look at, versus many hyperproperties may actually talk about an unbounded number of traces. More recently, Markus Müller-Olm has come up with a very interesting variation of this that also allows you to talk about asynchronous hyperproperties. by stepping with different speeds through the different copies in the new calculus expression. So this is a very cool direction. Yeah.
Okay, thanks. Armin.
Yeah, there were two questions in the chat before me, but maybe.
Sorry. I'm only looking at the
raised hands.
The raised hands. I'm really sorry. Yeah. So maybe you still ask.
Okay. Yeah. So my question was, is there a difference when you consider explicit or symbolic model checking, like satisfiability? Like for LTL, classical LTL, there's no difference, but for CTL there is a difference. And for you?
You mean in performance of the model checker?
Like complexity.
What do you mean by that?
I mean, if the model is given symbolically, right, like as a sequential circuit, but you gave the complexity, the characterization in terms of states, right? There's an exponential gap, and for LTL, usually in the classical way, this doesn't make a difference, but maybe for you it does. So that's why I'm asking.
Oh, that's an interesting question. I would say that, well, it probably plays out in different fragments, but say in the quantifier alternation free fragment, it should behave exactly as for LTL. But whether once you have the power of quantifier alternation, whether you can sort of alleviate the impact of a multi-component representation, that's a very interesting question. I would imagine. I shouldn't speculate. It's an interesting question. Yeah.
Maybe I quickly read out some of the questions from the chat. Maybe the first one from Ranjit Yala. How can the repair program be equivalent if it satisfies a different set of properties?
Oh, by equivalent, I just meant some sort of relation on the traces. For example, you might be interested in a system that has a subset of the traces and yet satisfies non-interference or so. So, I mean, often the repair problem is stated in this way, that you're allowed to eliminate non-determinism from the system in a way that satisfies certain properties.
And then maybe as a last question from Yannick Moy, have you applied your tools for checking non-interference in software? There's more to the question, but maybe you can read that later. But
okay. Okay. So the honest answer is no, because that's actually not that easy. We have applied it to smart contracts and other types of software that's not so real software. But there are a number of issues with going to software, and one of them is the asynchronous semantics. I mean, we're assuming that if you have multiple traces, that there's a common clock that lets you step through them simultaneously. And in software, you may not necessarily have that. So you need logics that are capable of asynchronous semantics. Also, of course, there are the usual problems with dealing with the infinite state space. So we haven't done that. Other people, of course, have. So there is a very nice paper, for example, by Azadeh Farzan. So she discusses all these issues. How do you align two copies of a software in a clever way, such that the resulting self-composition is easy to verify and so forth. So there is some work in this direction, but it's still young, in my opinion.
Lots of challenges ahead. Thank you very much, Bernd. I would advise you to look at the chat. I mean, Ranjit has a long list, so you can interact together afterwards. So
Thanks very much for the questions.
Yeah.
Very nice.